Now let's look at the discrete Fourier transforms continuation of what we have studied in the previous session. As we have understood, DFT is basically computation of a discrete time series where the sequence which we generate in a discrete Fourier transform is again finite. When it is continuous, we call it as discrete time Fourier transform, which you have seen a lot earlier. Now let us look at this discrete Fourier transforms. What are its properties? And then let's try to solve some problems in this session. Okay, let us read this. The discrete Fourier transform computes the values of the Z transform for evenly spaced points around the unit circle for any given sequence. Okay, if the given sequence to be represented is of finite duration, that is only finite number of non-zero values, the transform used is discrete Fourier transforms. Let us see this. For example, let us say I have a discrete series like this. Okay, let us say this is having values 0, 1, 2, 3, 4. Okay, this is a sequence 1, 2, 3, 4, 5. There are 5 in this, so this is the sequence. When I have such a type of specific series given to us, then I will go for discrete Fourier transform. Okay, that means in an earlier case of discrete time Fourier transforms and Fourier transforms, whenever you do a summation either from minus to plus infinity, or you do an integration which is from minus infinity to plus infinity. That means here this is a continuous spectrum. Okay, whether it is in time domain or frequency domain, this is continuous. Now when I look at something which is finite and which is not exactly tending from minus into plus infinity, then you have to use a discrete Fourier transforms. Okay, so when you look at this type of sequences given to you, always ensure that we go for a DFT. Later we will see how DFT can further be optimized, that we can see later, but now whenever you have such sequences, you go for a DFT. What are the applications? Where do I use this DFT? Basically, DFT used in digital signal processing specifically, like linear filtering, correlation, and spectrum analysis. All these things we use DFT. And there are various versions like fast Fourier transform and different types of fast Fourier transforms. What are the different algorithms used? So DFT is the beginning of the analysis of any spectrum, particularly in digital signal processors. Now let us look back at what we know earlier so that we can build up what are the advantages or what is the use of actually using a DTFT. So let us look at a continuous time Fourier transform. As you are aware, continuous Fourier transform x of j omega is given by, as I told you now, it is integration from minus infinity to plus infinity x of t e to the power of minus j omega t dt. Okay, and when I calculate the inverse Fourier transform, what happens? 1 by 2 pi, again the integration is from minus infinity to plus infinity x of j omega e to the power of j omega t d omega. So the point you have to understand from this slide is the summation or the integration which we are doing here is from minus infinity to plus infinity, and when I want to calculate the Fourier transform of it, or when I calculate the inverse Fourier transform also, the integration has to be done from minus infinity to plus infinity. Now when I look at the discrete time Fourier transform of again a discrete time signal like x of n, x of e to the power j omega is given by integration minus infinity to plus infinity x of n e to the power of minus j omega n. This is what, or this is how we get a discrete time Fourier transform. Again, the point that is very clear is the integration is from minus infinity to plus infinity. So the terms which are going to get are continuous in terms of the omega, that is frequency. Whereas you can still calculate x of n, that is inverse discrete time Fourier transform, that is given by 1 by 2 pi x of e to the power j omega e to the power j omega and d omega. So this also produces a continuous spectrum of x of n. So you take a discrete series x of n, and when I calculate the discrete time Fourier transform, I will get a continuous spectrum. So when I say spectrum, it is in the frequency domain. How do I get a discrete time Fourier transform? It is derived from x of n by performing the sampling operation in both time domain and frequency domain. So the DTFT of a discrete time sequence x of n is obtained by performing the sampling operation in time domain only. If you remember, we have seen how convolution is done. Okay, so convolution again is nothing but where you take the x of n weighed by a certain delta function. So this is also the discrete time Fourier transform of a discrete time sequence x of n is obtained by performing the sampling operation in both time domain and frequency domain. That's very important. And the DTFT is of a discrete time sequence x of n is obtained by performing the sampling operation in time domain only. Now let us slowly move on to DFT. Okay, as I have told you earlier, let us take x of n, which is a finite duration sequence. X of n is finite duration. It's not tending to 0 to infinity or minus infinity to plus infinity or 0 to minus infinity. It is a finite sequence. Then how do I calculate the DFT? So n is the points used to represent the discrete Fourier transform, and we use the capital letter N for it. Expressed as x of k is equal to n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi n k by n, where k is equal to 0, 1 up to n minus 1. So let us see this little on the board. Now what I'll do is I'll take a discrete sequence. This is a finite sequence. The duration of this is finite duration. Okay. Then the DFT is represented by capital X again, and we are using k here. So we are following a certain notation from the beginning, isn't it? So we are using for the transform into another domain from the time domain, we are generally representing it by a capital letter. So we're taking x here, and then this is a x of k is what we use for a discrete Fourier transform. What is the formula given here? It is given that this is a finite series. So it will be n is equal to 0 to n minus 1. So what is the summation here? The summation is from n is equal to 0 to n minus 1. That is, we have, how many points we have? We have n points here. So this is called as an n point. This is called an n point DFT. So I have a finite duration sequence, and in fact the DFT also is of finite duration. That is, it is an n point where n is from 0 to n minus 1 summation. So n is again a finite one here. Okay, so this is how we do. So this is very important here, and the formula is x of k is given by the summation n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi n k by n, where k is from 0 n minus 1. I'll just show you how we can do this type of how to visualize this type of DFTs. So let's say that k is equal to 0 first. So this will be x of 0. Okay, so it will be summation from 0 to n minus 1. Let us take n is equal to 3. So that is what are the values it can take? It will take 0, 1, 2. So total value, so 3. Okay, let us see this. So x of 0, how do I calculate? So it will be the summation of all this. So it will be, what is n now here? Starting with n is equal to 0. So it will be 0. E to the power of, again this will be 1. Then similarly x of 1. Okay, 0, 1, then you put on this whatever the values of this, then again you put on this and whatever values of this. So you have to take for all these three values, 0, 1, 2. And again here you have to take care of k. Okay, k is equal to 0 here, k is equal to 1 here, k is equal to 2 here, and so on. Okay, because n is equal to 3, you have to, this will stop, the summation will end at k is equal to, that is n minus 1. So this is how we do the discrete Fourier transform calculations. And of course, when you have a discrete Fourier transform, there must be an existence of inverse discrete Fourier transform. Now how do we calculate the inverse discrete Fourier transform? In the inverse discrete Fourier transform, summation is x of n is equal to 1 by n, summation of k is equal to 0 to n minus 1, x of k e to the power of plus j 2 pi n k by n, where n is equal to 0, 1, n minus 1. So this is inverse discrete Fourier transform. So that since the summation, the n is to be changed to k. Now let us represent, because in all the factors where calculating x of k and x of n, we have used a factor called as e to the power of minus j 2 pi by n in the formula, isn't it? So let us use a factor called as w. So what I'll say, w is equal to e to the power of minus j 2 pi n. This w is called as Twiddle factor. It's called as the Twiddle factor. Now the DFT and the IDFT can be represented in terms of the Twiddle factor. So what is x of k now? The summation of k is equal to 0 to n minus 1, x of n, wn, kn, k is extending from 0 to n minus 1. So we have just seen e to the power of j minus 2 pi kn by n has been replaced by the Twiddle factor. So this is what you get, and similarly I can also calculate what is my x of n is equal to 1 by n, summation again to up to n points, that is n minus 1, x of k, wn minus kn, where k is equal to 0, 1, n minus 1. Okay, this is how we can simplify DFT by using what is called as Twiddle Factor. Once I know what is the Twiddle Factor, that is W, n is given by minus j2 pi by n, we can just rewrite the equations for DFT and also for IDFT. Now let us look at some of the Fourier transform, discrete Fourier transform properties. As we have been seeing, the properties play a very important role. The properties help us in identifying what are the different characteristics of your transform, whether it is a Fourier transform, whether it's a discrete time Fourier transform or whatever. This will give you an idea about how your transform is behaving and what are its characteristics. The second point that helps us in knowing the properties of any transform is we will be able to simplify any problems which are given to us. So given a bigger problem, the solution becomes actually little easy when I apply the properties of it. On that note, let us see what are the properties of your DFT. Okay, there are so many properties here for DFT. Let us start reading one by one. But let us just find out what are these properties. Okay, the properties of DFT are, the first one is periodicity. Okay, the periodicity property is a very important property of discrete Fourier transform. And tomorrow when I have to optimize or find out some other method which is faster than DFT, then this periodicity property helps us in developing an algorithm which actually computes DFT series at a faster rate. We call that as a fast Fourier transform, that we'll look at in future sessions. Then comes the famous property, that is the linearity property. Third comes your shifting property. Then the fourth property is the time reversal of a sequence, because we are looking at a sequence of numbers, sequence of points, sequence of data. So we look at what is the time reversal of a sequence property. Then look at a circular time shift property. Similarly, we look at a circular frequency shift property. Then again the famous, which we have been seeing different properties, complex conjugate property, which is being applied to different transforms like Fourier transforms. So that again complex conjugate property we'll look at. Then we look at what is called a circular convolution. Then we look at what is called as a circular correlation. Then we'll see what is multiplication of two sequences, what is the property of it. And finally, we'll look at Parseval's theorem. So all these 11 properties are very important in DFT. As I've said, knowing these properties helps us in identifying important properties which help us in removing redundancy or any time consuming operation which we are doing in DFT that can be reduced. Let us look at these properties in detail. Let us start with the first property called as periodicity. Before that, let us just write down how does the inverse discrete Fourier transform and the discrete Fourier transform exist. Let us just identify this is applicable to all the Fourier transform properties. So given x of n, what is its discrete Fourier transform, that we will see here. See here, we have taken x of n as a discrete finite duration sequence. This is having a discrete Fourier transform. Let us write down here discrete Fourier transform. What is how many points this has? This is an n-point sequence. So let us put that n-point sequence also here. That is given by x of k. Okay. For any property for us to read, we start with the statement saying that x of n, a discrete time series finite sequence, has a DFT which is x of k, which is of n point. So this is assumed. So this does exist for all our properties to be discussed. In that vein, let us see the first property of DFT now. So what does the first property say? The first property is called as the periodicity. Let us see that. Statement of periodicity. If a discrete time signal is periodic, then its DFT will also be periodic. Also, if a signal or sequence repeats its waveform after n number of samples, then it is called a periodic signal or a sequence, and n is called the period of the signal. So as is obvious here, if the input x of n is periodic, then if I calculate the DFT of that, that will also be periodic. And then if a sequence repeats every n times, isn't it? So it's, let us say n is 2 here, 0, 1. Then after that it repeats again. So 0, 1 again repeats after n. So then this we say it as the sequence is having a period which is equal to n. So this is the property of periodicity. Let us look at again the famous linearity property. So what does this linearity property say? If x1 of k and x2 of k are the n points DFTs of x1 of n and x2 of n respectively, and a and b are arbitrary constants, either real or complex values, then x1 of n multiplied by a plus x2 of n multiplied by b will have a discrete Fourier transform which is equal to a x1 of k plus b x2 of k. So as I have said, let us see this. This is existing. Okay, so let us say I have x1 of n, let us say its DFT, endpoint DFT is x1 of k. Okay, so this is existing. Then similarly I have x2 of n, this is DFT, and again this is endpoint, this is having x2 of k. Okay, this is what we have. Then let us say there are two constants a and b, they can be either complex or real. When I weigh them, that means now a x1 of n, okay, so this is weighed by this factor, plus b x2 of n will have, as you see here, individually x of n is having x1 of k, its DFT, and we know that this is also having x2 of k, the other one, x2 of n. So when I am multiplying with a certain constant here, even if I calculate the DFT, that also will be carried on there. So this is what is called as a linearity property. Let us look at the shifting property. Let us first start with the statement. Let xp of n be a periodic sequence with a period n, which is obtained by extending x of n periodically. That is, xp of n is nothing but x of n which is periodic. So you can write this as xp of n is equal to L is equal to minus infinity plus infinity x of n minus L of n. Let us now shift the sequence xp of n by k units to the right. So just understand this. It says xp of n is nothing but a periodic sequence x of n which is repeating with the period n. So xp of n can be written as summation of L is equal to minus infinity plus infinity x of n minus Ln. Okay, let us now shift the sequence xp by k units to the right. So what happens? So we can write this as xp dash of n. What is xp dash of n? Xp dash of n is xp which is shifted to the right by k units. So you can write this as xp dash of n is equal to xp of n minus k, and that is equal to L is equal to minus infinity plus infinity x of n minus k minus Ln. Then the finite duration x dash of n can be expressed from xp dash of n, that is x dash of n is equal to what? Xp dash, when it is existing from 0 to n minus 1 only and it is 0 elsewhere. So this is what is this property about. Then this is obtained by x of n by what is called as a circular shift, and the period of this is capital N. Okay, that's the shift. The circular shift of a sequence can be represented as the index of modulo n, that is x dash of n can be written as x of n minus k mod of n. So we can just represent that like that. So x dash of n I can write as x of n minus k mod n. So this is your circular shift. When I do the circular shift, this is what you get here. Let us see some other property called as time reversal of a sequence. Okay, so again, as I said, x of n for this property to be satisfied, we have seen that x of n there exists a DFT x of k. So therefore we open the statement with that particular point. If x of n is having a DFT of x of k, then x of minus n mod n is equal to x of capital N minus n, which is having a DFT of x of k comma mod n, that is x of n minus k. So what does this property say? This property is when I have an endpoint sequence in time is reversed, is equivalent to reversing the DFT values also. Okay, so let us just see this on the board. Now let us take, this is the time reversal. So instead of taking plus n, I am taking minus n, and this is mod fn. Okay, this is nothing but x of n minus n. So if x of this is having a mod, I mean a DFT of x of k, then what will happen to x of k? That means the DFT of this, that will be equal to x of n minus k. That means if there is a shift in time, there is a time reversal in time domain, in DFT also there is a reversal here. Let us look at the other property called as circular time shift. Okay, so what does this property say? This property states that if the DFT of x of n is x of k, then x of n minus L mod n will have a DFT which is equal to x of k e to the power of minus j2 pi k by n. That is, shifting of the sequence by L units in the time domain is equivalent to multiplication in the frequency domain by a factor e to the power of minus j2 pi k by n. So let us see this. So what is that this property says? Property is x of n minus L here. As you see here, there is a shift here, and this is mod n. When I do this shifting, then what will happen to the DFT? The DFT, this invariably gets multiplied by a factor. X of k is already there, and this is multiplied by a factor minus j2 pi k by n. So this is the multiplication factor in frequency domain. So when a sequence is shifted, as you see here, this is shifted by a factor L here, then the output in the DFT will in effect be a multiplication by this exponential factor e to the power of minus j2 pi k by n. Let us see the other property. It's called as a circular frequency shift property. We have seen a circular time shift property earlier. Now we'll see a circular frequency shift property. So what does this property say? Again, x of n is having a DFT x of k. Then earlier we have shifted the time domain sequence by factor L in time circular shift, which resulted in multiplication by e to the power of by a factor e to the power of minus j2 pi k by n in the frequency domain. Now let us see exactly the reverse of this. So this means that when a sequence x of n is multiplied by the complex exponential e to the power of j2 pi n by n, it is equivalent to circular shift of the DFT by L units in the frequency domain. So the similarities you can see, we have shifted in time domain L units, so it was e to the power of minus j2 pi n by n multiplication in the frequency domain. And now when I shift the frequency sequence by the same L units, it will be multiplication by a factor e to the power of j2 pi n by n in the time domain. So this is the circular frequency shift property. Let us look at the complex conjugate property of this. So this property states what? That I have an x of n which is having a DFT x of k, then x star of n, that is complex conjugate x star of n, will have a DFT which is x star of minus k mod n, that is x star of n minus k. So this is the complex conjugate property. So what does this say? X star of n will have a Fourier transform again which is complex conjugate equal to this. So this is my complex conjugate property statement of DFT. Let us look at another property called as circular convolution. So what does this property say? Again, the opening statement, x of n is having a DFT x of k. Then if x1 of n will have a DFT x1 of k and x2 of n is having a DFT x1 of k, then x1 of n and x2 of n will have a transform DFT which is equal to x1 of k, x2 of k. Here n indicates circular shift by n points. So this is the circular convolution property, where x1 of n and x2 of n denotes a circular convolution of sequence x1 of n and x2 of n, and is expressed by this equation. What is that equation? x3 of n is equal to m is equal to 0 to n minus 1 summation x1 of m x2 of n minus m mod n, and that is equal to m is equal to 0 to n minus 1 x1 of m x2 of n minus m mod n. So this is how we get a convolution. So let's just see this. If circular convolution says x1 of n is having a DFT x1 of k and x2 of n is having a DFT x2 of k, then when x1 of n is circularly convolved with x2 of n, that is indicated with the capital letter n, that will be having a DFT which is equal to x1 of k and x2 of k. Okay, that means x1 of n and x2 of n. Okay, so circular convolution means I'll put a capital N here. So this is circularly convolved with a sequence. Then this will have a DFT which is equal to x1 of k and x2 of k. So this is how we do in the case of this is what the property of circular convolution says in DFT. Okay, let us look at the other property called as circular correlation. So what does this property say? This property says that for a complex valued sequence x of n and y of n, where x of n is having a DFT of n points x of k and y of n is having a DFT y of k of n point sequence, then Rxy of L, that is the circular correlation, is given by the formula Rxy of k, that is capital, is equal to x of k multiplied by the complex conjugate of y star of k. Okay, so this is what is the circular correlation property is about. So here let us take, this is what this circular correlation says, is x1 of n is having x of k and y of n is having y of k. Then circular correlation, let us say Rxy of L, okay, and is DFT. Okay, all these are DFTs, and again of sequence n, sequence is n here. So this also will be having a DFT and again sequence of n, and we are using this notation here Rxy of L. Okay, now how to calculate the cross correlation, circular correlation of this? That is nothing but this is equal to x of k, product of x of k and y star of k. So this is an important property called as circular correlation property of DFT, where Rxy of L is an unnormalized circular cross correlation sequence and is given by summation of from n is equal to 0 to n minus 1 x of n y star of n minus L mod n, that is Rxy of L. Okay, let us look at the other property called as multiplication of two sequences. So what does this property say? x1 of n again is having a sequence x1 of k in DFT. So that is x1 of a is having a DFT of x1 of k of points n, and x2 of n is having a DFT of points n again, that is x2 of k. Then if I multiply x1 of n and x2 of n, what will be its DFT? That's what this property says. So what is that? That is equal to 1 by n x1 of k multiplied by x2 of k. So this is very easy to remember. When I multiply in time domain, its DFT will be division by that n points and the product. Okay, so if you multiply this x1 of n, x2 of n, then this will be equal to 1 by n x1 of k, x2 of k. Okay, so this is the multiplication of two sequences. When I multiply two sequences here, and see here the summation again is divided by 1 by n points and x1 of k and x2 of k. This is the multiplication property. Now look at the final theorem, final property of DFT called as the Parsevals theorem. So what does this Parsevals theorem says? This theorem says that for a complex valued sequence x of n and y of n, again with the statement that x of n is having a DFT of n point sequence x of k and y of n is having a DFT of n point sequence y of k. Then this property, we have to just read this. So what is that? It says that summation n is equal to 0 to n minus 1 x of n y star of n is equal to 1 by n summation k is equal to 0 to n minus 1 x of k y star of k, where significant inputs have been taken from the earlier property also here. So let us see how can we relate this to a Parsevals theorem. So what we have done here is, if the sequences y of n and x of n are same, then what happens? Summation will be equal to n is equal to 0 to n minus 1 x of n whole square. Okay, that is nothing but in DFT it will be equal to 1 by n summation k is equal to 0 to n minus 1 x of k whole square. So this expression relates the energy in the finite duration sequence x of n to the power in the frequency components x of k. So when you want to have a relation between energy and power, this is a perfect place. On the left side you see the energy in the finite duration of sequence x of n. There is a relation to this to the power in the frequency components of the x of k. So this actually gives a relationship between the energy components on one side to the power components on the other side. So time domain energy is related to frequency power in the frequency components of x of k. So this is Parsevals theorem.